does the word degree mean? The what? The highest exponent. Bless you. Yes, the highest exponent. Okay, so differences in the degree of the numerator and denominator can cause changes in the graph of a rational function. Horizontal asymptotes is what this whole lesson is about. Technically, the horizontal asymptotes are describing the end behavior of the graph, like where are the two furthest ends headed to. So if we look at the first one, what is the degree of the numerator? Degree, the highest exponent in the numerator. The highest exponent, nerd. 1. The highest exponent I see in this numerator is a 1.
Oh, I thought you meant out of
What about on the denominator? Is it infinity on the denominator?
2.
2. Good. Okay. So if we look at the graph, looking at where the ends are headed, okay? The graph on this one, it actually has a horizontal asymptote here. That's where the two ends are headed. As it goes right, it's headed towards 0. As it goes left, it's headed towards 0. Yes, Nick?
That looks like it's going below the asymptote.
It is. You'll see that on the next one also. We'll talk about that. Do y'all want to write out the technical end behavior? Do you want to write that out? Do we want to, or do we just want to say that as it goes right, it goes to this, as it goes left, it goes to this?
Okay, yes.
Okay. All right, as it goes right, where are the y values headed? To 0.
Down.
No, it doesn't go down forever. It goes to, as it goes right, where are all those y values headed?
The asymptotes are different.
The y values, not the x values. Where are the y values headed? As it goes to the right. 0. Yeah. As it goes right, the y values go to 0. As it goes left, where are the y values going? To 0. Goes to 0. And as Nick pointed out, it looks like this one actually crosses and goes underneath that horizontal asymptote. It does. We have been lying to you. What? Yeah. You actually are allowed to cross a horizontal asymptote. You're never allowed to cross a vertical one. We'll talk more about this on Friday. You are allowed to cross a horizontal asymptote because technically it only describes the end behavior. So that's why sometimes we just call it an end behavior asymptote so that people are not like, yeah, you can't cross that. Because it just tells me where the two ends going. They're both eventually headed to 0. All right, and then I changed it. I adjusted the degree in the numerator. What is it now? 2. And the degree on the denominator is also a 2. And look, is the end behavior still going to 0? This one, I know it's kind of hard to see it on this graph because this is a zoomed out Desmos graph. The end behavior asymptote on this one is actually at 4. And you can definitely see it crossing the end behavior asymptote on this one. You can see it crossing here because it really just describes where are the ends headed to. The ends, eventually those y's are going to end somewhere around 4. Eventually the y's are headed towards 4.
Oh, so it did below, but it's still heading to
Yes, as it goes left, it's still going to that 4.
Oh, okay.
This
So it's as long as it's headed towards the direction of the 0.
As it goes right, it's going towards 4. As it goes left, it goes towards 4. I hate writing the end behavior like this. I love a good technical end behavior. So yes, you might get some crossings in the center of your graph as long as the two ends are headed towards that asymptote. What changed on this one is now the degree of both the numerator and denominator are the same. The degree of both the numerator and denominator is the same. Degree of top and bottom are the same. This is actually what we did last time when we found the horizontal asymptote. Because if you remember last time we did the ratio of the leading coefficients. And what would be the ratio of this leading coefficient? 4 over 1, which is what our horizontal asymptote's at. It's at 4. All right, and then we get into some crazy ones on the last one.
3 and 2.
Degree of the top is 3. Degree on the bottom is 2. And this one actually does not have a horizontal asymptote. It does still have an end behavior asymptote, but we don't really refer to it as horizontal. The asymptote on this one is actually slanted. It's what's called an oblique asymptote. Oblique, we'll learn more about that tomorrow. So the asymptote on this one is actually kind of diagonal through your paper, like right here. Again, we'll learn more about this tomorrow, how to find it. It's like a linear function asymptote. So theirs would be its little asymptote. You can also cross these asymptotes because they do just describe where the ends are headed. Okay, so as it goes towards the right, where are the ends headed on this one? Infinity, yeah. As it goes right, oh, you finally got the answer. As it goes right, it goes towards infinity. Okay. As it goes left, where's the end going? Negative infinity.
So if we say goes, are we talking about like x?
Yeah, as x goes. Yeah, if you trace your finger along the graph to the left, it's going to go to negative infinity. What changed on this one? On this one, we made the degree of the top bigger than the degree on the bottom. Degree on the top is bigger. Specifically bigger just by 1 degree. Degree on the top is bigger. When you take pre-cal, you'll look at what happens when the degree on top is bigger by 2. Guess what type of asymptote that one is? It's a quadratic asymptote, yeah. None of those this year, though. I know. Okay. So, So doing a quick little rundown about the 3 possibilities for end behavior horizontal asymptotes now. Okay. If the degree is bigger on the bottom would be like the very first graph here. If the degree is bigger on the bottom, your horizontal asymptote is always going to be at 0. If the degree is bigger on bottom, then the HA is at y equals 0. If the degree is bigger on the top, that's like the 3rd graph we had. 3rd graph. What type of asymptote was that one again? Slanted. Slanted. Oblique is a technical name. I always remember the oblique muscles right here. Guess what they are? They're slanted. They're slanted muscles. Then it's slanted, which is an oblique asymptote. And then the one that we're used to already, this is the one we had when we were graphing last time. If the exponents are the same, then it's going to be the ratio of the 2 leading coefficients. It's going to be y equals a over c. Then it's y equals a over c, which is just the ratio of leading coefficients.
Which is going to be h8, right? So if it's the same, it's just the same thing as we figured.
Got ourselves a little acronym to help us remember this, and because I know sometimes people are like, how am I going to remember these 3 possibilities? Okay. BOBO. Technically that's BOB0. BOB0. You see how it looks slightly different? Because BOBO means bigger on bottom. What's the HA at?
0.
0. Bigger on bottom, 0. Bigger on... I know, y'all think it's funny, but people come back and be like, well, I remembered it, Miss Brody, on my pre-cal test. Bigger on bottom, 0. BOTS, what do we think that stands for?
Bigger on top?
Bigger on top? Slanted. Good. Although the last one's hard to guess.
Ratio of leading coefficients? Strain.
Okay. And then the last one is the one that's usually hard to guess, but once you hear it, you're like, oh, okay. If the exponents are the same, so like if the degree is the same, if the exponents are the same, divide coefficients. If the exponents are the same, divide coefficients. Exponents. Do it along with the unit circle, along with a squared plus b squared equals c squared. Divide coefficients, yeah. I think the calculus teacher says BOB0 BOTS instead of saying bots for slanted. She says BOTS because none. There is technically not a horizontal asymptote. There's a slanted asymptote. But I like the S. It helps remember that it's slanted. Y'all ready to try some? 2 graphs. We got this. So we are finding the vertical and horizontal, aka in behavior asymptote. We're also going to find the x and y intercept. This first one is not pretty. It's not pretty. Get ready. You'll see why. Okay, step 1. We're going to try and factor it. The top just barely factors. What could I do on the top? You could take out the 5. Technically, you really don't need to, but just in case, maybe there's something that'll cancel. So take out your 5. Okay, bottom, we got an easy factoring. Okay, so did I have a factor cancel? No, no factors cancel. So what do I know about holes?
No holes.
None. Bummer. I love when there's a hole because then it gets easier. It's an easier function, but oh well. Okay, so no holes. Moving into vertical asymptotes, that's where the denominator equals 0. And if I have 2 factors in the denominator, how many vertical asymptotes am I going to have? 2. Good job, Nick. You're starting to just visualize it. So x, 1 at x equals 5, 1 at x equals 1. The horizontal, aka end behavior asymptote, we're going to look at the degrees of the numerator and denominator. What is the degree on the top? 1. What's the degree on the bottom? 2. So the degree is bigger on the bottom, which means it's at 0. Bigger on bottom, 0. Okay, and then lastly, finding the x and y intercept.
So that would be 5x minus 2 equals 0.
Is that 5 going to be affecting anything?
No, it's going to be just 0.
Yeah, technically you could just divide by 5 right here, and you just get x minus 2 equals 0, which means x equals 2, but as an ordered pair, it would be
X equals 2. Or 2 comma 0.
2 comma 0. Good job. Almost got you. The y-intercept, when you plug in 0 for x, again, you can have a choice of where to plug it in. You can plug it into the original, the factored one, because they are both equivalent. Let's see. So we'll have y equals 5 times 0 minus 2. 0 minus 5, 0 minus 1. So that'd be 5 times negative 2, which is negative 10. And on the bottom, we'll have negative 5 times negative 1, which is positive 5, which would simplify to negative 2. So then as a point, that would be 0, negative 2. Okay. Here's the bad part about having 2 vertical asymptotes. I'm going to flip back to the front so you can see. These 2 on the front both had 2 vertical asymptotes. This one has 2 vertical asymptotes, one here, one here. The second one has 2 vertical asymptotes, one here, one here. When there's 2 vertical asymptotes, how many branches does the function have? 3 branches, which means you need 3 points, because you got to have at least 1 point per branch. And do we have 3 points? No. So we know we're definitely already going to have to find another point, at least 1, maybe more than 1. All right, let's put all this on our graph. I have a vertical asymptote at 5, another one at 1. And I have a horizontal asymptote at y equals 0. Which, remember, the horizontal asymptote, you can technically cross those. It just describes where the ends of your graph are going. It's the end behavior of your graph. And we'll see that in just a brief second, because what are we about to plot?
point.
A point that's on that asymptote that we just graphed. I have an x-intercept at 2, 0, which is right here on the in behavior asymptote, which is allowed as long as the ends of my graph head there. And then I have a y-intercept at 0, -2. Okay. So this left branch, I can draw that. I know what that's going to look like. It's going to be curved like a normal branch looks like we saw last time. It's going to head towards the horizontal asymptote this way. It's going to head down towards the vertical asymptote this way.
So we need another point for
We need another point for the branch that's on the right, though. I do have a branch somewhere over here. I just got to find a point that's on it.
Wait, so with the one that's in the middle on
We'll
the
talk
X,
about that. We'll talk about that.
that's
Yeah.
this one?
We'll talk about it. We'll talk about it. Okay. For our extra point, we need to plug in something that's bigger than 5 to get a point over here. Which I want to plug in? 6. Sounds great. Okay. I literally wrote down a 5 even though y'all said 6. Okay. We can plug it into the original. We can plug it into the factored one. We should get the same answer both ways. It doesn't matter. I'm going to plug it into factored one. So I'm going to have a 5. And then I have 6 minus 2, which would be a 4. Bottom I have 6 minus 5, which is a 1. 6 minus 1, which is a 5. So that's 20 over 5, which is 4. So I have a point at 6, 4. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Okay. The one in the middle, though, is where we're going to have some. We could probably need to find another point to figure out which way this one is coming from. Because, let me use my scratch paper to kind of show you what your options are for this. Okay, so when you have two vertical asymptotes, in the middle you're going to have one of 3 options. You might have something that looks like upwards facing, kind of janky looking parabola. It might look like that. Or you might have something that looks like a downwards facing kind of janky parabola. Looks like that. Or you might have something that looks kind of like a snake. So a snake that goes through here. Now I can tell this is a snake one because I have a point that crosses that horizontal asymptote. But I don't know which way the snake comes from. I don't know if it's a snake that comes from this way, crosses, and then goes down. Or maybe it comes from this way and crosses and goes down. So I need to find one more point in between these two vertical asymptotes to just figure out where's the snake coming from. Did it come from the left cross? Does it come from the right cross? One more point. What should I want to plug in this between here?
3.
Maybe 4. 4 would be a little
4.
further. I'm going to do 4. We could do 3. It doesn't matter. But. Okay. 5 times, and then 4 minus 2 would be a 2. Let's see. 4 minus 5 would be a -1 on the bottom. 4 minus 1 would be a 3 on the bottom. So that's 10 over -3. Is that what y'all got?
Yep.
Okay. Which is -3 and a third, if you're trying to think where you're going to graph that at. 4, -3 and a third. 1, 2, 3, 4, -1, 2, 3 and a third. So this kind of gives me an idea of what the snake should look like. It's going to go up and not allowed to cross that vertical asymptote. As it goes down, it's going to kind of snake and just not allowed to cross that vertical asymptote going downwards. Pretty, right? You can lie. You're like, no, it's not pretty.
It's so pretty.
The next one's pretty, though.
I think I like this one.
I know. I like rational functions. I like how technical they are. They all look different. All right, for the next one, we're going to start by doing factor it. Good. Because we got to check and see, is there a factor that's going to cancel?
It'd be x minus 3x.
We have had this one all day long.
Oh, yeah.
Yeah, we've done that one twice already. This will be a 3rd time. Okay. And then,
The bottom one.
bottom one needs to be 2 numbers that multiply. Bless you. -4, +2.
Oh, we have a hole.
There's a hole in the graph. Ding, ding. What is the x value of that hole? Is it always going to be at -2? No, it is today though, but hole at x equals -2. I'm going to write out my new and improved reduced function that I need to remember to use to find everything else. I'm going to highlight it because the old one is dead, the new one is alive. How do we find the y value of the whole?
You plug in -2
To
the new one.
To the new function. Good. So on the top we'll have -2 subtract 3. On the bottom we'll have -2 subtract 4, which is -5 over -6, which is 5 over 6, which is like almost 1 if you were thinking of where it's going to be graphed. 6 over 6 would be 1. How many vertical asymptotes am I going to have?
2 bigger.
Vertical asymptotes.
Divide coefficients.
Vertical asymptotes. 1. Why are we only going to have 1, Liz?
Because it's just,
There's only one factor in the denominator. Because remember, you need to set the denominator equal to 0. I'm going to take x minus 4. I'm going to set it equal to 0. And that gives me what? X equals 4. Okay, my horizontal asymptote. This is the one where you got to think, is it BOBO, is it BOTS, or are the exponents the same?
oh, use that for the horizontal one.
Mm-hmm. Eats DC. The exponents are the same, so we divide the coefficients.
So it'd be 1 over 1.
Excellent.
Oh, no. Yeah. 1 over 1. Eats DC.
Okay. Lastly, my x-intercept and my y-intercept. Alright, x-intercept, that's when y is 0. You know your denominator is always going to cancel when you multiply it, so you can just set your numerator equal to that y that's 0.
X minus 3, x equals 3.
And then this is the one we want to write as a point. Very good. 3, 0. And then lastly, the y-intercept. Plugging in 0 for x.
So that'd be 0 minus 3, 0 negative 3 over 4, which is 3 over 4.
Which is 3 over 4. So that would be the point 0, 3/4. Alright, everyone catch up and then we'll graph it together. Alright. So I'm going to graph my 2 asymptotes. I have 1 vertical, 1 horizontal asymptote. Vertical asymptote is at 4. 1, 2, 3, 4. Horizontal asymptote is at 1 because that was the ratio of the 2 leading coefficients for this one. We have 3 points that we can graph. Technically 1 is a hole, so we graph it looking like a hole. So when you graph -2, 5, 6, literally draw it like as a hole in your graph, an open dot. -2, 5, 6 is like right underneath this little asymptote here that's at 1, because 5, 6 is just slightly under 1. Well, I also have my x-intercept and my y-intercept. Are those both on the same one? 1, 2, 3, 0, 3. Dang it! They're all 3 on the same branch. I'm going to use all 3 of these to graph the branch, though. So when you go past the hole, it just kind of skips over it. Skips over it, continues towards the asymptote, skips over it this way. And yes, we will have to find one more point on the right side to find an accurate point over here.
So around 7 or so?
1, 2, 3, 4, 5, 7 sounds good. So plugging in 7 to my new and improved function. On the top I'll have 7 minus 3. On the bottom I'll have 7 minus 4. So that's 4 over 3. 1 1/3. Okay, so 1, 2, 3, 4, 5, 6, 7, 1 1/3. We have a point. We're going to use that 1 point to graph that branch. And then before you put your notes away, let's do the domain and range on this one. Alright, domain. So remember, we're writing our domain and range in set notation for these.
So that would be
There's actually two numbers that we need to exclude when we write the domain. We obviously need to exclude the vertical asymptote.
which is 4.
What other x do we need to exclude? The whole, the x of the whole. So we're going to say x is a real number, but we want to say it's not 4, and it's also not -2, because that's the whole. This one was the vertical asymptote. Similar for the range. We want to say it's a real number, but we want to exclude the horizontal asymptote. So we want to say it's not 1, and it's also not whatever the y value of the whole was. What's the y value of the whole?
1
5/6.
5, 6.
5, 6.
I was looking at all the wrong numbers.
It's okay. More often than not, if you're going to forget anything on the domain and range, you're going to forget this whole number, so try and remind yourself